In previous sections, we assumed our data follow a standard statistical model, a mean structure plus random error. But assumptions are just that, assumptions. They are not guaranteed. The entire purpose of model adequacy checking is to validate whether our chosen model is reasonable for the data we actually collected. In previous sections, we assumed our data follow a standard statistical model, a mean structure plus random error. But assumptions are just that, assumptions. They are not guaranteed. The entire purpose of model adequacy checking is to validate whether our chosen model is reasonable for the data we actually collected. This slide lays out the roadmap. We're not checking assumptions randomly, we follow a sequence. Is the mean model correct? Are there outliers? Are errors independent? Do we have constant variance? Are the errors normal? Residuals are the key diagnostic tool for all of these checks. A residual is simply the difference between what we observed and what the model predicts. If the model is correct, residuals should behave like random noise. Importantly, residuals are estimates of the true error terms, so studying residuals is how we indirectly study the errors. Raw residuals aren't always comparable because their variances may differ. That's why we scale them. Standardized residuals divide by an overall estimate of variability. As a rule of thumb, most scaled residuals should fall between -3 and 3. If they don't, that's a red flag, often for outliers. This is where the linear algebra sneaks in. The hat matrix maps observed data to fitted values. It literally puts the hat on Y. Why do we care? Because the diagonal elements of this matrix, the H values, tell us how influential or extreme each design point is. Here we see something important. Residuals are correlated and have unequal variances. This is normal in regression and ANOVA. It explains why naive residuals can be misleading, especially at extreme design points. Residual variance depends on H. Points near the center of the design space tend to have larger residual variance. Points far away have smaller residual variance. Ironically, model violations often happen at these extreme points, making them harder to detect unless we adjust for this effect. Studentized residuals fix this problem. They scale each residual by its own standard deviation. This makes all studentized residuals comparable, regardless of location in the design space. This is why studentized residuals are preferred for diagnostics. A residual plot is just residuals plotted against something else: fitted values, factor levels, time order, or normal scores. The choice of what goes on the x-axis depends on which assumption we're checking. In a good residual plot, we want randomness. No patterns, constant spread, and centered at 0. Patterns mean structure, and structure means the model is missing something. This slide is meant to train your eye. When you see curvature, funnels, clusters, or trends, that's evidence against one or more assumptions. Learning to recognize these patterns is more important than memorizing formulas. Model fit is about the mean response. If the mean model is wrong, then everything else collapses. Lack of fit doesn't mean your analysis is useless, but it does mean your conclusions are only approximate. Lack of fit often shows up as non-random structure in residual plots. It can also appear when residuals are systematically large for certain factor levels or omitted variables. This is why plotting residuals against everything you can think of is often helpful. Outliers are observations that don't behave like the rest of the data. Large studentized residuals are your first clue. But remember, an outlier isn't automatically wrong. It's just unusual. If assumptions hold, studentized residuals follow a standard normal distribution. That gives us probability-based cutoffs. Anything beyond plus or minus 2 deserves investigation. Beyond plus or minus 3 is very rare. Never delete an outlier automatically. First, analyze the data with and without it. If it changes conclusions and is due to experimental error, remove it. If it reflects real behavior, then the model is the problem, not the data. This example will anchor the rest of the discussion. We have 4 battery types, multiple observations, and a time order. This gives us a perfect case study for outliers, independence, and variance issues. Here is the residual plot versus the factor levels. What do you notice? A studentized residual of -2.98 immediately stands out. That's not something you ignore. Investigation revealed a data entry error. This is exactly why diagnostics exist. Here is the data after the correction. Once the error is corrected, the residual structure improves. This highlights an important lesson. Diagnostics protect you from blindly trusting flawed data. Independence is critical because it underlies constant variance and normality. We check it by plotting residuals against run order. Trends, cycles, or drifts suggest dependence. One person inflating all balloons introduces fatigue and learning effects. That's a textbook violation of independence. The design, not the analysis, is the real issue here. Here is the residual versus order plot. You can see here that the learning effect that we spoke about is evident. Dependent errors are hard to fix after the fact. If time effects exist, we can model them explicitly using ANCOVA or time series methods. But prevention through good design is always better. After adjusting the model to include the time variable, we no longer have the structure in the residuals. Normality is assessed using normal probability plots of studentized residuals. Minor deviations are usually fine. What we really worry about are heavy tails and extreme outliers. ANOVA is robust to small deviations from normality, especially with equal sample sizes. Outliers and heavy tails are the real enemies. Transformations or non-parametric methods are your backup options. Based on the plot, it seems that the residual do hug the line. This would indicate that the normality assumption is valid. This is also evident since the p-value on the normality test is not significant. Equal variance is required because we pool variance estimates. Funnel-shaped residual plots are a classic sign of trouble. Formal tests exist, but plots are usually more informative. If the largest variance is more than 3 times the smallest, that's usually unacceptable. This rule is simple, practical, and widely used. Here we go back to the battery example. Only this time we will use the lifetime as the response variable instead of lifetime per cost. Switching to lifetime instead of cost-adjusted lifetime reveals a major variance problem. The variance grows dramatically with the mean. This screams, transformation needed. We can see this issue somewhat in the residuals versus fits plot. Then again in the residuals versus type. We can create an ANOVA type test for the variances by setting up the test as all of the variances are equal versus at least one variance is not equal to the rest. So what do we do about this? Well, usually the issue is with the variance increasing with the mean. We can take care of this with a variance stabilizing transformation. The goal is to find a transformation that makes variance roughly constant. This usually means identifying a relationship between the variance and the mean. We can use the equation on the slide to accomplish this. But how do we find Q? By regressing log variance on log mean. The slope tells us which transformation to use. This gives us a data-driven way to choose a transformation instead of guessing. These are 2 theoretical considerations based on known relationships for 2 discrete distributions that are often used. One is binomial and one is Poisson. The estimated Q suggests a square root transformation is reasonable and interpretable. Practical meaning matters. We don't transform just to satisfy math. Usually we will adjust to get a standard transformation. In this case, 0.366 is close to 0.5, which allows us to use the square root. After transforming, we start over, recheck all assumptions. And remember, your conclusions now apply to the transformed scale. After implementing the transformation, we again look at the residuals versus fits. Based on the plot in the slide, it seems the problem has been fixed. These methods exist but should be a last resort. They are approximate and less powerful than working with a well-chosen transformation. Random effects models add one extra assumption. The treatment effects themselves must be normally distributed. This is checked using treatment averages. This diagnostic is weak unless you have many factor levels. With only a few treatments, don't overinterpret this plot. Now that we know how to validate models, we're ready to trust our inference. Next time, we'll focus on inference for one-factor experiments.